Okay.
Okay, can you see the screen?
Okay. So yeah, we can see it.
Yeah.
And so let's start. So we are now going to start the presentation, the defense of Automata. Here in the committee, we have today myself, which is the advisor, Professor Marcos, and also Dr. Michael Cipriano. Doctor, right? Yes, congratulations. So yeah, so you can start. You are going to have 20 minutes, at most 20 minutes to present. After that, the committee is going to ask some questions, and then in the end, we're going to have a reserved session where we're going to discuss the result of the examination. So good luck.
Okay, so I'll start. Again, my name is Arthur. I will present my partial in bachelor thesis, which is titled Footstep Planner for a Humanoid Robot Based on Model Predictive Control. These are the topics I will talk about today. Pardon me if it will be like a very short overview, since there is a lot of ground to cover, a lot of topics to cover. But starting with the motivation, today there is an increasing presence of robots in the daily lives of humans. And legged robots especially, they have several advantages since they are capable of traversing rough environments and traversing different obstacles. They don't have to, for example, they can cross over different obstacles, so they're a lot more versatile, but they are a lot more complicated. And these robots also have a need for precise movement and positioning. So the robot will need to be where it expects itself to be, right? So that everything works accordingly. So just a brief overview of the problem that I will be tackling in this thesis. It was first the formal presentation was by Dietz and Tedrick in a master's thesis, which is from an initial state x0 and a target set of states xf. An ordered sequence of footstep positions s1 to sn should be found such that following it will lead the robot safely from one initial state to one final state inside the set of states. This is what I based myself. I studied the thesis by Dietz and Tedrick, but it is not exactly what I want to tackle. So the actual problem I will be tackling is given an initial state and a final state, which I currently have as the center of mass positions. They could be very well adapted to be the foot positions. Find an ordered set of footsteps, S1 to Sn, that when followed will safely place the robot center of mass at XF. Again, this could be fairly easily the foot positions instead of the center of mass. The set S of footsteps should be such that it minimizes both defined objective function and the control horizon n, which in practice happens when you minimize the objective function. Okay, so some context. This thesis spawned as a work from the Soccer 3D team from Ethan Drives. Ethan Drives is the robotics team from ITA. The Soccer 3D team is one of the leagues in the RoboCup, and it is a very good platform for performing model predictive control, or in general control and reinforcement learning research, since it has completely simulated physics. So the robots are simulated as closely to the real world as possible. And this robot that is used in this league is the Aldebaran Now, which you can see here on the right side and in the video. Okay, so the objective for the thesis is to use an MPC-like approach to create a program that is capable of providing an optimal solution for the footstep planning problem I presented earlier, while still respecting constraints from the robot's physical characteristics, such as maximum and minimum joint positions, and the environment. So we don't want, for example, a foot to be inside a certain obstacle, because it will obviously not be able to do that. The program will receive as input the current position of the robot and an objective, and then will generate the footstep plan. Depending on how much you know about the problem, this key phrase here might not make much sense, since we often want these things to run at a fairly high frequency, since the robots have to do in real time planning. But this works is part of a master's thesis in which we will address the time constraints. Okay, so some literature I had to study to be able to do this thesis. So Vukobratovic and Kajita the first one presents the zero moment point stability criterion, and the second one the 3D linear inverted pendulum model. They are both fairly common starting places for most of the research around humanoid walking. They're very commonly found in a lot of different works. Professor Maximus' master's and doctorate applies control methods to generating humanoid robot gaits. It was a very good starting point to understand everything I needed to learn. It was to start learning about humanoid walking. Tedrake and Dates uses the mixed integer optimization to generate the footstep plans. Acosta and Posa here as well. They use it. Dates and Tedrake is I would guess, the major inspiration for this thesis. Because they showed for the first time that, hey, this can be done used mixed integer optimization and a control approach. Afonso and others is what I base myself on to implement a minimum time control to minimize the footstep horizon. And Dr. Cipriano here presented a planner capable of performing adjustments to the planned footsteps, which it gave me a notion of like state of the art, what is happening currently, and helped me understand also how to model the problem. Okay, so very brief control theory, given a state X and a state matrix X and a control matrix X at time step K. The idea is to solve an optimization problem that minimizes the cost function J, subject to a process model, which you can see here, which is a function of the state matrix X and its control matrix U. And this has to be subject to the state and control variables, constraints for the state and the control variables. Okay, so a short overview on mathematical programming. Which is something we will use along with control theory. Mathematical programming is a broad term that refers to optimization problems. It includes linear programs, mixed integer programs, and disjunctive programs. So a lot of the optimizations that have to be done for model predictive control, the minimization of the cost function, they fall under the umbrella of mathematical programming. So we can use a lot of the techniques that have been developed for mathematical programming to perform this optimization and to make it faster. One such technique, which will be used in 2 cases, which I will talk about later on, is Big M, which is a technique to transform the disjunctive constraints, so a set of OR constraints, into equivalent mixed integer linear constraints, which is this system of equation and inequations here. So this is not very easy to code when you are doing the numerical optimization, and this is a lot easier. So it just helps to transform these constraints into something that is computationally tractable. Okay, so minimum time control, which is one of the applications for the Big M technique. As I said, I learned this through Afonso et al. So the idea is to guide the problems to the desired state in the minimum amount of time possible. To do this, we use binary variables in the Big M technique. The idea is to add a binary variable to each time instant in an objective function, which you can see here, and then enforce a terminal set of constraints at every instant along the fixed time horizon t. So at every xk or xk plus 1, xk plus 2, we say that these states are equal to the terminal set of constraints. And then later on, we use the Big M technique to relax the constraints, as you can see here. And since the binary variables in the Big M technique that are used here are inside the cost function, they will also be minimized, which leads to the minimum horizon possible. Okay, so I'll talk a little about Kasadi. Kasadi is an open source numerical optimization tool, which has an emphasis in optimal control. In the scope of this thesis, it is used extensively to formulate the optimization problems from the footstep planning problems, and then to solve them. Kasadi is the tool that I'm using to do basically all the heavy lifting and to provide all the solutions. Here is an example for problem modeling using Kasadi. I want to model this objective function, and I want to optimize it subject to these set of constraints. So you can see here on the right that it is very fast to do this. You just set the variables here, explicit the minimize function, set the constraints, set it to minimize, and then choose a solver. So Kasadi has a lot of different optimizations algorithms or a lot of different solvers. The implemented interfaces by default are these and others, so SNOPT, WOR, HP. But the one we are most interested in is IPOPT, which is the interior point optimizer. It is included by default in Kasadi, and it is, according to them, the most extensively used. Some details of the implementation for Kasadi are on the thesis from Veshta, and it solves problems of this form, which is very similar to what we want. So we have constraints on the state variables, and we have constraints that are derived from the state variables, so a function of the state variables. Some very brief concepts about humanoid walking. On the top here, you can see the cycle that our robot has during its gait. These three here are the double support phases, and these two are the single support phases. During the single support phases, the foot that is moving is termed the swing foot, and the foot that is at a standstill is termed the support foot. The support foot in single support and in double support, in all cases, it defines the support polygon. So here you can see the support polygon on the single support, and here on the double support, it is, mathematically speaking, it is the external hull of all the points in contact with the ground. And the support polygon is important for the zero moment point stability criterion, which I referred to earlier, which means that the zero moment point, being very short here, which is the point in the foot where the foot floor reactions are being applied. If it is inside the support polygon, the robot will be stable, so it will not topple over. So it is, as I said before, a very important stability criterion, which is very widely used in academia today. So from these concepts, we want to use them later on to define, hey, where can we place the robot's foot, right? So currently, the approach that I have deemed the most interesting is to define an admissible region through mostly inverse kinematics. I will talk a little about this later. Where the foot can be placed, and then to later on simplify this so that the constraints can be placed on the position of the foot. And to do obstacle avoidance, so to not place the robot's foot, the planner, not place the foot inside an obstacle. This is the second application of Big M. The idea is that since there is an obstacle, the foot has to be in this case, since it has four sides, in region R1, R2, R3, or R4. So this corresponds to this disjunctive constraint, and this disjunctive constraint can be converted into these linear constraints. Okay, so the robot platform I will be using for this work, as I said, it is the Aldebaran Now, which is the robot using the Soccer 3D Simulation League. Some of the specificities of the Aldebaran Now are mostly the hip yaw pitch joint restrictions. So the hip yaw pitch joints, they have a single motor that commands them. So both joints, the left and right joint, they have to be relative to the center of mass. They have to have the same value when opening. This is a physical constraint that will be one of the first important constraints when considering the placement of the foot. So along with this, here in the right, you can see which joint I am referring to, the hip yaw pitch. And along with this, I intend to do the mapping of the footment placing, as I was mentioned in the slide earlier, through mostly inverse kinematics. So to have a model from the robot and to map the different ZMP points at the edge of the support foot to a foot or to a region on the right, and then to find this admissible region where the robot will not topple. And relative to the foot, this region should be mostly constant, so it doesn't have to shift around a lot. Okay, so this is some of the results already. I need to be able to do the optimization. There needs to be a model for the problem. There are two different models that I have adopted currently. The first process model, which I already have implemented, is based around having 6 different variables. First off, the footsteps are modeled in successive timestamps. So this means that each footstep happens at a timestamp. So t plus 1, t plus 2, t plus 3, t plus 4. And the first process model has a total of 6 variables for the state, which are the x and y and theta variables for the right and the left foot. And the so the control matrix has 3 variables, which are the x, y, and theta displacements for the swing foot. So how much that foot moves. However, this model has a problem, which is that in the state equation there is the presence of sort of a binary matrix that commands which foot is moving, since the control matrix doesn't differentiate this. But this, since it's not interesting to have a lot of different binary variables when the optimization is being done, uh, it is interesting to remove it. So this can be done while modeling inside Casati. So the restrictions to left and right steps are different, a little different, and then you can remove the binary variables. The second process model is a lot smaller. I haven't implemented this yet. It is one of the objectives I have, but the state variables now only have 3 variables. So they are for the support foot, and the control variables then are the positions of the swing foot. So it's not the displacement anymore; it's the actual position. So the state equation then becomes a lot more simpler, since it's just the support foot would, in the next time instant, in the next footstep, will be this the swing foot. So again, it is modeled in the same fashion as before, so with the successive timestamps. Okay, so a conclusion here. Again, this is the formal definition of the problem here, which I have presented earlier. Again, for the minimization to occur, there needs to be an objective function. And the objective function that I have considered currently is just the difference, the quadratic distance from x, y, and theta of the center of mass to the objective position. This again can be changed to be just the foot positions, the quadratic difference from their objectives. But this is the objective function for the first model, and this is the objective function for the second model. So again, just the center of mass positions and the objective. Here are some partial results. On the left here, you can see some of the preliminary results. These are from very early versions of the program. This first one I implemented, it had some manner of obstacle avoidance, but it didn't consider the footstep angles. So it was superseded by others. This one is a later version, and you can see here already that each point on the graph represents each foot position, so left foot and right foot, and this here represents an obstacle. And the arrows represent the angle of the foot. But in this later version, you can see that there is a problem here where the robot keeps the planner considers that the robot is able to cross each foot, which is obviously not true. So these 4 images on the right here are from the current version of the program, and you can see that it has mostly solved this issue. Here is these 2 bottom images are some in these situations, the robot is starting at the same point and heading towards the same point, but the swing foot first is the left and the other one is the right. So you can see here that in one of the cases, the robot is able to shuffle towards the objective, and in the other, it's just it cannot do that, so it has to move around a little. But you can see from these 4 images that they are considerably better than the earlier versions here. Okay, so some planned results. So some milestones for the thesis is the first one is to implement a planner using the second process model. The second is to simplify some of the nonlinear restrictions that I'm currently using. I haven't mentioned this a lot, but some of the restrictions I am using currently, such as this one for the obstacle avoidance, they are very nonlinear, and it is not interesting because it is very computationally expensive. So the second milestone is to simplify these. And the third milestone would be to implement a minimum time formulation into the planner, as I discussed before. And depending on time availability, there are other milestones that I want to accomplish in this thesis. As I said, this is part of a master's work. So there are a lot of things I want to include, but as a starting point, as a midpoint to be more accurate, these three milestones are something I considered that would be a good point to start my master's thesis. And thank you. Those were 20 minutes roughly. And if you have any questions, feel free to ask them.
So thank you, Arthur. It was exactly 20 minutes. Congratulations. So now we are going to start the part where the committee is going to make questions. So first, we are going to start with Dr. Mikel, who is our external member here. So I thank you, Dr. Mikel, for taking your time to evaluate the work. So thank you very much.
Thank you.
And feel free to ask any questions that you want.
Thank you for the presentation. I think it's a very good work so far. And yeah, I had a few questions, more curiosities, I think. The first one, I've seen that also, like you have some pieces of code that you've put in the presentation and the manuscript, and so you have 5 footsteps in the horizon, right?
Okay, so actually the implementation that I have, you specify how many footsteps you have in the horizon. So okay. The current implementation, you can in these images, you can see that this one, for example, probably has some more footsteps, but the user can just specify how many footsteps he wants in the horizon. This is how it's implemented currently, but the idea is to remove this and to just have the minimum time formulation later on.
Okay, I see. Thanks. And how much is this problem? How much does it take for the solver to solve this kind of problem? Do you have some statistics about this, or?
Just a second. I have to pull up the solver here. From what I remember, it was a couple of milliseconds, I think. I just don't have it ready at the moment.
Yeah, it's okay. No, I just wanted to understand the magnitude of the time, just out of curiosity. And yeah, also, I'm not sure I understood the difference between the two cost functions. Can you explain it?
Yes.
Again?
The difference is they are essentially the same, right? Mm-hmm. But the state and the state variables, the state matrix, it changed from the first formulation to the second one. So the first formulation has the left and right foots, okay. And in the second one you just have the support foot. So
okay, I see.
Essentially, the cost function is the same, but it's a function of, in the first case, it's just the state, and in the second case, it's the state and the controls.
Okay. And regarding the mixed integer part, I think like you're using it for the admissible region, let's say, where the foot can be placed, and so my understanding was that you are using a union of convex sets, right? And depending on the value of the binary variable, one of these sets are used, right? Is it like that, or?
Yes. So the idea here is, for example, in the case of obstacle avoidance, we have the obstacle. So there are a lot of different semiplanes from depending on how many sides the obstacle has.
Yeah.
So the object has, in this case, are semiplanes, right? So the foot can be placed in the different semiplanes. So it's the an or constraint, as I said before.
Okay. And okay, yeah. Okay, thanks. Yeah, I understood. Perfect. Yeah, I don't think I have any other questions. Maybe if I have some, I will ask them later. But
Okay, sure. Sounds good.
congratulations for the work. I think it's a very good work. Thanks for the presentation.
Okay, thank you.
Thank you very much, Dr. Michael. So now I'll make some very brief comments. So first of all, congratulations on the amazing work, Artur. I know Artur since his first year of engineering when he entered the robotics group at Androids. So he has worked with me for a long time. And he has also been very diligent, worked very well. And during the thesis here, he also worked very well. And it's only 6 months right now, right, of the
Yes.
undergraduate thesis. Yeah, we started with the masters before, but mostly like reading some papers. But the actual work, it's only 6 months, and you already have results. This is amazing. And so congratulations on that. About the comments of Dr. Michael, yeah, I think that you're right about the things that you asked. And about the time, it's taking a couple of milliseconds, as Arthur said now. But probably when we add everything, like the minimum time formulation and everything, is going to take a whole lot of time to compute. But our idea is that, so we had another work in the past, and actually, I remember Nicola was part of the committee of this work, where he used a neural network to copy the result from the solver to a neural network, and then after you do that, it becomes very fast. So our idea here is about forget about the computation time, let it be very slow, but let's try to solve the planning problem the best that we can do. And after that, let's try to imitate that using a neural network. And then with the neural network, it's probably going to take 1 millisecond or less than that. And okay, you can say, okay, but you don't have guarantees with the neural network. But we don't give a shit because it's going to be working for robot soccer. So if it fails, it's not a big deal. If it works like 95% of the time and then 5% it fails, it's not a big deal. So for robot soccer, that this solution is perfect. So this is the idea on the long run. Okay, so now I open for questions from the other people here. Deodato, do you want to make any question?
No, just want to congratulate Arthur for their work and you there. It's very interesting, and it sounds very difficult to achieve all these results. And I know the control and walking is not a easy thing to do. Congratulations.
Okay, thank you.
Okay, nice. So now we go to the reserved session. So to make things easier, I created another meeting room. So Mikael, if you can go there, it's going to be very fast.
Yeah, sure, thanks. So do we have to close this session? I think you are muted. I cannot hear you.
Okay,
Yeah,
sorry.
muted.
yeah, it was muted. Sorry. Yeah, you can stay here, but then you need to mute yourself. Just
Okay.
mute yourself here and go to the another one. Okay, Arthur, after some discussion there, it was a bit tough, but in the end, we decided that you are approved. So congratulations.
Okay, thank you.
So let's just take a picture. Smile. Okay. Okay, thank you all.
Okay, thank you very much for participating.
Thank you.
Thank you. Bye-bye.
Thank you. Bye,
Congratulations
guys.
on the doctorates.
Thank you, guys. Best of luck
Bye-bye.
for everything. See you. Bye-bye.
You too. Bye-bye.